It might seem like a bit of a jump to the left to start talking about gas laws straight after we just finished talking about circular motion. It's kind of an odd topic in terms of the rest of what we're doing. So we're kind of talking mainly about motion, mechanics, dynamics in modules 1 and 2. We're talking mainly about electricity and electromagnetism in module 3 and also some assessment. And we're talking about modern physics, radioactivity, quantum relativity in module 4. And gas laws doesn't really fit neatly anywhere. Part of the reason for that is we're kind of assuming that you already are very across the particle model, that solids, liquids and gases are made out of particles. Their temperature determines how fast the particles are moving, and the different states relate to different relationships between the particles and all of that kind of stuff, because we really start that, I think, in senior primary. So really the specifics of this they're in the syllabus, and it's an interesting topic, but it is kind of off by itself a little bit. There's a lot of gas law stuff in chemistry around stoichiometry, so people who are doing chemistry will use this more, but it is part of physics as well. So the notion of an ideal gas, sorry, got to turn the clicker on before you use it. The notion of an ideal gas is actually a concept. We sometimes kind of loosely talk about real gases as though they're ideal gases. So helium is a good approximation of an ideal gas, but it's not an ideal gas, because an ideal gas isn't ideal, it's a philosophical concept. So what's that concept? Particles of zero volume, so mathematical points, no length, no width, no depth, zero volume, very far apart, moving very fast, and not exerting any forces on each other. No attractive or repulsive forces, no internal structure. So they're not kind of dumbbell shaped and hit in different directions. They are points that collide like points, bounce off the walls, bounce off the container. So there are various gases that approximate real gases. As I say, helium, because it's monatomic, it goes around as He1, not say H2 like hydrogen, where it's got this diatomic structure. So it's small, it's approximately spherical, or we think about it that way at least. The particles are very light and have very little force on any other particles. So helium's probably our best approximation of an ideal gas. But in fact, if we keep the pressure relatively low and that atmospheric pressure fits that, then most gases pretty much behave like ideal gases. Using the ideal gas approximation is not going to mess us up by very much. There'll be errors some decimal places down for most gases. But obviously the less ideal gas-like, so something like propane, C3H8, is obviously quite large, quite massive, has some internal structure, is likely to have electronegativity and bonding and differences in the attraction between the particles and so on. Like it's really only butane, it's really only a step or two from liquid. So you sort of see, you sort of mean that obviously there are better and worse approximations to the ideal gas ideal concept. The temperature is a measure of the average kinetic energy of all the particles. Some are going fast, some are going slow. It's a random stochastic process. They are bouncing off each other and off the walls of the container and losing energy to each other, gaining energy from each other and so on. But there will be an average overall of that kinetic energy of the particles, and that's the temperature of a gas. So when the gas heats up, particles are moving faster, higher velocities. When the same mass, higher velocity, so higher kinetic energy. When the gas cools down, the particles are moving more slowly on average, but there'll be still a wide range of motion. Pressure is the sum of the collisions of the particles with the wall of the container. So there will be a whole bunch of collisions happening all the time, and the ways in which they collide, that's causing the actual pressure. So pressure, temperature and volume are related, and gas laws, which is what we're talking about, are ways of describing that. PV equals nRT, the ideal gas equation or the ideal gas law. So in other words, to get to this equation, you need the assumptions of the ideal gas concept. This works for an ideal gas. It works more or less well for various real gases. And we can use it most times. So pressure, volume, number of moles of gas involved. So you can see we're already kind of on the edge of chemistry. The ideal gas constant, which we have to be careful of, I'll talk about in a sec, and the temperature. Temperature should always be in kelvins, not degrees Celsius or degrees Fahrenheit. So degrees Kelvin, it's not degrees Kelvin, it's just Kelvin. So temperature should be in Kelvin. Volume can be in cubic meters or liters or various other units, and pressure can be in bar or torr or atmosphere or pascal or kilopascal and so on. So the value of R, like the value of R that I have in my head is 8.314, and that's for pressure in kilopascals and volume in liters. Depending on the kinds of units you choose, the value of R will change. There's another one that's, I think, 0.082 something something for different units. So when you're actually looking up a value of R in a table, it depends what units you're using for pressure and volume, which value of that constant you should use. So it's not a particularly easy one to always pick the right constant. Boyle's law and Gay-Lussac's, I think GUY is Guy in French, so I don't know, Gay-Lussac's law. These three all relate various of these variables, pressure, volume, and temperature, in different ways. So Boyle's law basically says the pressure times the volume, the product of the pressure and the volume for a particular sample of gas, is constant. What does that mean? If you increase one, you have to decrease the other to keep it constant, right? If you rearranged that, if you leave that equation as it is, if you make the pressure bigger, then the volume has to get smaller to keep the total, that product constant. So for a particular sample of gas, if we change the pressure or the volume, we can use P1 V1, the initial pressure and volume, equals P2 V2, the final pressure and volume, to figure out what happened. So if I have a particular container of gas and then compress it, make it smaller volume, then the pressure is going to go up. And that makes sense. Like we know that if you put more pressure in your car tire, the pressure goes up. In other words, you're decreasing the volume from outdoors into the tire. Charles' law similarly relates volume and temperature, but it's an inverse relationship. So if one goes up, the other has to go up to keep it constant. If you increase the volume, you have to also increase the temperature to keep everything else the same. If you decrease the volume, you have to decrease the temperature. So V1 over T1 equals V2 over T2. And Gay-Lussac's law relates pressure and temperature in the same way. Now, you could memorize all of those, and we kind of remember those gentlemen's names, but I find it's much simpler to just remember the combined gas law, and then you can just basically remove whatever's irrelevant. So if you remove temperature, if you're not changing the temperature, if we just pop back, you end up with Boyle's law, right? If you take that bottom line of temperature off, you just end up with P1 V1 equals P2 V2. If you remove pressure, you end up with Charles' law, and if you remove volume, you end up with Gay-Lussac's law. So, as I say, the simplest thing in any calculation is to just know this one and PV equals nRT, and pretty much you're set, because you can basically use those.